Here we have another hypothesis testing question. We can see that towards the end of the question it does indeed involve hypotheses, and that suggests that we'll be able to use binomial distribution earlier on in the question. So over a long period of time, 20% of bowls made by a particular manufacturer are imperfect and cannot be sold. So as usual, I'm just picturing a whole load of bowls that have been made, and 20%, that's 1 in every 5, are going to be imperfect, and they're the ones that can't be sold. At first, all we have to do is find the probability that fewer than 4 bowls from a random sample of 10 made by the manufacturer are imperfect. So first of all, setting this up using the binomial distribution, we've got that it's 20% of the bowls that are imperfect, and in this question it's a random sample of 10 bowls. The thing we're interested in is the number that are imperfect. So I'm going to let x be the number of imperfect bowls. So x is going to have a binomial distribution where the two parameters we need to give, n is 10 and p 20%. So we've got n is 10, 20% is 0.2. So moving on to actually answer the question, we're looking for the probability that fewer than 4 bowls. So I can write that, the probability that x is less than 4. Now, cumulative probability tables give values less than or equal to, not strictly less than. So what I like to do is just draw a little number line. So because we've got a 4 in the thing that we're looking for, I would write down a 4 and the numbers before and after 4. So in this case, 3 and 5. Now, fewer than 4 means I can put a dividing line before the 4. What I want is everything before that. So the values I want are everything less than or equal to 3. So looking up on the tables, I can now do that to find the probability that x is less than or equal to 3. So if I find the tables and I go to the page where n is 10 and I'm looking at the probability of 0.2, and I'm looking for x to be less than or equal to 3. So looking in the appropriate row and column, I find the value of 0.8791. So that's my probability that I'm going to write down. Now I haven't rounded it, I usually just write from tables to show that my answer is a value that's 4 significant figures because it has been taken from the tables. So, moving on. The manufacturer introduces a new process for producing bowls. To test whether there's been an improvement, each of a random sample of 20 bowls made by the new process is examined. From this sample, 2 bowls are found to be imperfect. I need to show that this does not provide evidence at the 5% level of significance of a reduction in the proportion of imperfect bowls, and I need to show the hypotheses and calculations clearly. Now, that's a lot of information given in that question. A few things to watch out for. We've now got a random sample of 20, so instead of using n is 10, I'm now going to have n is 20. Now, looking at the wording in the question, they're talking about making an improvement, so this is suggesting a one-tail test. They're not saying the process has changed the proportion of faulty bowls, where it could have changed to be a greater proportion or a smaller proportion. They're actually saying that we're looking for a reduction in the proportion of imperfect bowls. So that's going to affect my alternative hypothesis. When we have a one-tail test like this, where we've got a clear direction that we're going in, then the null hypothesis will be p equals. The alternative will either be p strictly less than or p strictly greater than, not p is not equal to, as we'd have with a two-tail test. So let's get that written down. What we're saying is for the null hypothesis that p is the probability that we were given in the question, so 20%. We're going to look at our sample and see whether it gives us evidence that in general it's still 20% of the bowls that are imperfect, or there's actually been a reduction in the proportion. What we don't want to do is look at this result and say, oh, that's 2 out of 20, and use 2/20 as our p-value. So p equals 0.2, 20%. That's what we're testing. Is the proportion still 20%? So our alternative hypothesis, in this case, because we're looking for a reduction, we're looking to see if the probability is now less than 20%. So less than 20% of the bowls being imperfect is what we're aiming to find. Now, what we've done is to write down two things about P. We need to be very clear about what P actually represents. So in this case, P is the probability of a bowl being imperfect, not just in our sample, but we're talking about in the population. So out of all the bowls made by this manufacturer, is it 20% that are imperfect? Now, I don't have to write my hypotheses in words, but I often do, simply because I can then refer back, especially to the H1, the alternative hypothesis, when I'm writing my conclusion. So the P equals, the null hypothesis would be the uninteresting situation that the proportion of imperfect bowls is still 20%, so no change there. The alternative hypothesis, though, using the wording from the question, it's that there's been a reduction in proportion of imperfect bowls. So, I like to start with a diagram showing this distribution. So here's my distribution. It goes from 0 bowls to 20 bowls, and I'm interested in seeing how many bowls would be so unlikely to be imperfect that we would suggest that we've got evidence that the proportion is not actually 20%, so that our p-value is not 0.2, but it's actually less than 0.2. So, sometimes I like to just think about the expected value. In this case, NP, 20 multiplied by 0.2, is 4. So I'm expecting the most likely number around here, I'm expecting about 4 bowls to be faulty if P is 0.2. So if I get less than 4 bowls, I might have some evidence that there's been an improvement. But how much less? That's what the test is going to do for us. Would it be enough just to have 3 bowls, or would it be 2 or 1 or 0? That's what we need to look up on the tables. So I go to the binomial probability, the cumulative probability tables. I go for n is 20, p is 0.2, and what I'm looking for is when we go from being less than 5% to more than 5%. And in this case, it actually happens within the first 2 values there. So what I've got is that the probability that x is less than or equal to 0 is about just over 1%, so that's less than 5%. The probability that x is less than or equal to 1 is the value of about 6.9%, so that's gone over 5%. So on my diagram that I've drawn, what I'm saying is that 0 is in the only value where the probability is still less than 5%. By the time I get to 1, my cumulative probability has already gone over 5%. So in fact, any number of bowls from 1 to 20, and I'll just have to accept H0. But if we find that in the sample there were no imperfect bowls, a value of 0, that would be enough to give us the sufficient evidence that perhaps H1 is happening. So, what do we do now? The critical region is the values which are in this shaded part, this least likely 5% of the time, and I've only got the one value, x is 0. My result, or rather the result given in the question, is that 2 bowls are found to be imperfect. So the result of x equals 2, well, that doesn't lie in the critical region. X equals 2 is in between 1 and 20, so it's in the uninteresting part where the result is not significant and we accept H0. When we make our final conclusion, we don't be quite as bold as to say there's definitely not been a reduction in the proportion. What we say is that there is not sufficient evidence to suggest, and then we want to do the wording of the alternative hypothesis. So in this case, the alternative hypothesis that there's been a reduction in the proportion of imperfect bowls, that's what we're looking for. So there is not sufficient evidence to suggest that there has been a reduction in the proportion of imperfect bowls. Now in the question, we were asked to show that this does not provide evidence, so we know the outcome we were expecting, and all this working is kind of backing that up. It said you should show your hypotheses and calculations clearly. So here are my hypotheses. That's the bit with the P's and this sentence underneath as well. And the calculations, that's these values, showing that with the 0 and the 1, that's how I've chosen my critical region. There is another way to do this by looking at the probability of getting less than or equal to 2 bowls, and we'd see that that's more than 5%. So that's another way of realising that 2 would not be in the critical region. In the mark scheme, the first part shows the values that I suggested. So saying that x has a binomial distribution, we were looking for the probability of x less than or equal to 3. And then there was actually a couple of marks for getting a binomial of 10, 0.2 and trying to add up the individual probabilities. That would take a little bit longer. So you could still get full marks by doing that. The hypothesis testing section, they've given the definition of what P is and the 2 parts of the hypotheses. They haven't actually said in the population, but recently the examiners have said they want to see that expression about P being the probability of something in the population. Now, this first section here is using the alternative method that I didn't really go through, looking at the probability of getting a value. They've said less than or equal to 3, but actually the way that I did it is down here, so using the critical region method. The critical region was 0 and the value was not in the critical region. So that's a perfectly valid way of showing the working for this question.